Welcome to Quantum Measurement, Lecture 7. This is your Professor Atif Fareed Mohammed in a series of quantum computing lectures at Marshall University in West Virginia. This module delves into process of quantum measurement, a crucial aspect of quantum computing. We will discuss the different types of quantum measurements, including projective measurements and generalized measurements, also known as POVMs. You will learn how to calculate the probabilities of measurement outcomes and how measurement affects the quantum state. We will also explore the concept of quantum decoherence, as we discussed earlier as well, and its impact on measurement accuracy. Emphasis will be placed on understanding the limitations of quantum measurement and the challenges of extracting information from quantum systems. In this lecture, we will have an emphasis on understanding the limitations of quantum measurement and the challenges of extracting information from quantum systems. So, in everyday life, measuring something is simple and harmless. We check the temperature of a room with a thermometer and the room is unaffected. Quantum measurement is fundamentally different. When we measure a quantum particle, we do not simply read off the value that was already here or there. You actually disturb the particle and force it to take on a definite value. Before the measurement, the particle was genuinely in multiple possible states at the same time. The act of measuring ends the situation permanently. This is not a limitation of our instruments. It is a deep feature of how nature works at the smallest scale. Imagine a person who's genuinely undecided between two options for lunch. They are not secretly leaning one way. The moment a friend asks, "So which one are you having?" the person commits to a choice. The question itself caused a decision before being asked. There was no single answer. A quantum particle, therefore, in reality, before measurement is similar. The question or the measurement creates the answer rather than just revealing one of the that was already there. Before a quantum particle is measured, it can exist in a superposition, a combination of multiple possible states simultaneously. This is not the same as saying we just don't know which state it is in. The particle is genuinely in all allowed states at once. We know this because when particles in superposition interfere with each other, they produce patterns. That would be impossible if each particle had secretly been in just one definite state all along. The superposition is real, and it ends the moment a measurement takes place. Think of a musical chord. When you play a C major chord on a piano, the sound is not secretly just one note with the others hidden. It is genuinely all three notes, C, E, and G, vibrating together at the same time. A quantum particle in superposition is like that chord. Measurement is like placing your hand on two of the strings and silencing them, leaving only one note ringing. The chord superposition is gone, and you are left with no definite outcome. Why measurement changes everything? Now, that's a good question, right? In quantum mechanics, the act of gaining information about a system always has a physical cost. To measure a particle, you must interact with it, bouncing a photon off it, applying a magnetic field, or connecting it to a detector. That interaction disturbs the particle. The more precisely you try to measure one property, the more you disturb another related property. That this is not a flaw in the detector. It is the law of nature. Information extraction and physical disturbance are inseparable at the quantum level. Imagine trying to find out where a marble is hidden in a completely dark room. The only tool you have is a flashlight. The moment you turn it on, the light touches the marble and slightly moves it. You found the marble, but now it is not exactly where it was. At human scales, this effect is too tiny to matter. For quantum particle, the flashlight disturbing the particle is unavoidable and significant. Every act of measurement carries a physical consequence. The two outcomes of measurement. Every quantum measurement does two things simultaneously. First, it produces a result, a single definite value, from the list of possible outcomes. Second, it changes the state of the particle to match the result. After measurement, the particle is no longer in superposition. It is now in definite state corresponding to the answer you received. If you measure the same particle again immediately using the same method, you will get the same answer every time. The first measurement locked the particle into that state. Imagine an election where voters are genuinely undecided until the moment they enter the polling booth. The act of voting forces each person to commit. Once a person has voted and left the booth, their choice is fixed. If you ask them again 1 second later, they will give the same answer. The particle after measurement behaves the same way. The superposition is gone and the state is now definite and repeatable. Measurement outcomes are probabilistic. The core idea here is that before measurement, quantum mechanics does not tell you which specific outcomes you will get. It only tells you the probability of each possible outcome. These probabilities are encoded in the quantum state of the particle. A particle can be in a state where one outcome is very likely and another is very unlikely, or in a state where both outcomes are equally likely. But no matter what the state is, quantum mechanics can never guarantee a specific outcome in advance, only the odds. A weighted coin has a 70% chance of landing heads and a 30% chance of landing tails. Before the flip, you cannot say with certainty what will happen, but you know the odds. A quantum particle is similar. Its state before measurement carries information about how likely each outcome is, but the actual result is always left to chance. Even a perfect quantum computer cannot predict individual outcome, only the probability distribution of many outcomes. Projective measurement. It's the most basic type. A projective measurement is the simplest and most common types of quantum measurement. It just asks a sharp yes or no question about the particle. Are you in this state or in that state? The particle must answer definitively. It cannot say a little of both. Projective measurements divide all possible states into distinct categories, like sorting colored balls into separate bins. Once sorted, the ball stays in its bin. The measurement is irreversible, and the sense that the superposition is permanently destroyed. Imagine asking a stranger, "Are you a morning person or a night person?" The question forces them into one of two categories. Before you ask, or before you have asked, they may have had mixed feelings and no clear identity either way. Your question has sorted them. Now, if someone else asks them the same question A moment later, they will give the same answer because the first question already forced the commitment. A projective measurement works exactly this way. It divided the quantum world into categories and permanently locks the particle into one of them. How projective measurements collapse the state? After a projective measurement, the particles no longer carries any information about previous superposition. The state has collapsed entirely into the specific outcome that was observed. This collapse is called wave function collapse or state reduction. All the weight that was previously spread across multiple possibilities is now concentrated entirely on the single outcome that occurred. The previous state is gone and cannot be recovered from the particle alone. Think of a jury that starts deliberation genuinely divided. 6 members lean towards guilty and 6 towards not guilty. The foreman calls a formal vote. Once the verdict is declared, the jury's opinion is officially collapsed to one answer. It does not matter that half of the room privately thought different before. The official record now shows only final verdict. The quantum state after measurement is like the official record. Only the final outcome survives and all previous ambiguity is permanently erased. Hopefully this is giving you an idea that how we live our human life and how we make decisions. However, usually we stick with the decisions which we have made during the course of our decision making. Measurement basis, choosing what question to ask. Every projective measurement is performed in a specific basis, a choice of which questions you are asking. Different questions reveal different aspects of the particle's state. Asking about spin along the vertical direction will give a different result than asking about spin along the horizontal direction. Crucially, choosing one question to ask means you automatically give up the ability to answer a different incompatible question about the same particle at the same time. The choice basis shapes what information you can extract. Imagine you have a photograph of a person. You can ask how tall are they, or you can ask how wide are their shoulders. So both questions can be answered from the photo, but the answer depends entirely on which question you choose. Now imagine that asking about height destroys the width information in the photo permanently. That is closer to quantum situation. The basis you choose determines what you learn, and certain other properties become unknowable, so you don't know them as a consequence. The uncertainty principle and measurement. Some pairs of properties in quantum mechanics are fundamentally incompatible. Measuring one precisely makes other irreversible uncertain. It technically makes other irreversibly uncertain. The most famous example is position and momentum. The more precisely you pin down where a particle is, the less you can know about how fast and in what direction it is moving. This is not because our instruments are imperfect, it is a fundamental law. Nature genuinely does not allow both properties to have sharp values at the same time. Imagine trying to take a clear photograph of a fast moving racing car. To freeze the motion, you need a very fast shutter speed, which requires bright light, but very bright light is a flash, and the flash captures position precisely but makes the speed blur irrelevant to read. If you slow the shutter to capture motion information, the position blurs. You literally cannot take one photo that gives you both perfect position and perfect speed at the same time. The uncertainty principle is nature enforcing this kind of trade offs and at the deepest possible level. Repeated measurements, what happens if you measure twice? If you measure a quantum system twice in a row using the exact same type of measurement, the second measurement always gives you the same result as the first. This is because the first measurement collapsed the state into a definite value, and the second measurement simply confirms that collapsed state. However, if you change the type of measurement between the first and second attempt, you can disturb the state again, and second outcome may differ from the first. Consider a spinning top that you stop and observe. Once it has stopped, checking it again immediately tells you that it is still stopped. But if after the first check you give it a nudge in a different direction before checking again, your second observation reflects the new nudge. The first quantum measurement is like stopping at the top. A second identical measurement confirms the stopped state. A different measurement is between is like a nudge. It disturbs the system, and the second results may no longer match the first. Generalized measurements going beyond sharp questions. Projective measurements ask sharp yes or no questions and give a definitive answer every time, but sometimes nature does not give us such a clean choice. Generalized measurements, also known as POVMS or POVMs, which stands for Positive Operator Valued Measures, allow for softer, more flexible kinds of questions. They can include outcomes like inconclusive or probably this but not certain. They are used when the system is not fully accessible, but when measurement happens indirectly or when we are willing to trade certainty for a broader set of possible conclusions. A doctor testing for a disease does not always get a clean positive or negative result. Some tests come back inconclusive. The signal was present but not strong enough to confirm. The doctor can report definitely sick, definitely healthy, or unclear, retest needed. A projective measurement only allows the first two options. A generalized measurement allows all three. This extra flexibility is powerful in quantum information science because it lets us extract useful partial information even when definitive answer is not available. The positive operator valued measures, what makes them different? The key difference between the POVM and a standard projective measurement is that POVMs allow for more than two outcomes that partially overlap in what they detect. The results that do not completely destroy the remaining quantum information. They are especially valuable when trying to distinguish between quantum states that are very similar to each other. Cases where projective measurement would often give misleading results. POVMs are designed to be the best possible strategy under those ambiguous conditions. Imagine you are handed a cup of coffee and asked to identify whether it came from cafe A or cafe B. The coffee states slightly different but are very close. A projective measurement is like forcing yourself to say definitely A or definitely B every time, even when you are unsure, and sometimes being wrong. A POVM lets you say this really tastes like A, this really tastes like B, or honestly, I cannot tell. You are sometimes inconclusive, but then you do commit. You are right. That is the advantage. Fewer errors at the cost of sometimes declining to answer. Quantum decoherence, the enemy of superposition. Decoherence is the process by which a quantum system loses its superposition because it interacts with its surrounding environment. Every quantum particle in the real world is surrounded by air molecules, photons, electromagnetic fields, and other particles. Even the tiniest unwanted interaction with any of these causes the quantum superposition to leak away. The particle effectively gets measured by the environment without anyone intending it. This is why quantum behavior is almost never seen in everyday large objects. They decohere almost instantly. Imagine, now again, let's get into our real life scenario. Imagine trying to maintain perfect silence in a concert hall so you can hear a whisper on stage. The moment anyone in the audience shifts in their seat, coughs, or breathes too loudly, the silence is broken. The whisper is drawn out. Decoherence works the same way for quantum superpositions. The quantum signal, a delicate superposition, is the whisper. The environment, air, heat, vibrations, stray electromagnetic fields is the noisy audience. Even a single unwanted interaction destroys the quantum state, just as single cough destroys the silence. So why decoherence matters? For quantum computing, the quantum computers store the process information in qubits, which rely on superposition and a related phenomenon called entanglement. Both of these are extremely fragile. Decoherence causes qubits to lose their quantum properties and behave like ordinary classical bits. When this happens mid-calculation, the answer produced by the quantum computer becomes wrong. This is one of the central enduring challenges building useful quantum computers. The calculations must be completed before decoherence destroys the quantum information being processed. Let's say, for example, if we are writing a complex equation on a whiteboard made of ice, the answer is perfect as long as the ice stays frozen. But the room is warm and the surface begins to melt almost immediately. You must finish writing and reading the answer before the ice melts completely and the equation becomes unreadable. Building a quantum computer that resists decoherence is like building a refrigerator powerful enough to keep the icy whiteboard frozen long enough to complete any equation needed. Decoherence versus measurement. What is the difference? Both decoherence and measurement collapse a quantum superposition, but there is an important distinction. A deliberate measurement is a controlled interaction designed to extract specific information. Decoherence is an uncontrolled interaction with the environment that destroys the quantum state without giving us any useful information in return. Measurement is intentional and informative. Decoherence is accidental and destructive. In a well designed quantum system, we want measurement but not decoherence. Think of a difference between a surgeon making precise incision and a child accidentally knocking over a glass of water onto a patient. Both disturb the patient, but only one is controlled, purposeful, and yields a result which is useful. The surgeon's cut is like a measurement, deliberate, informative, and contained. The spilled water is like decoherence, accidental, uncontrolled, and harmful. Quantum engineers work extremely hard to allow the surgical incisions measurements while preventing the spilled water or decoherence. Measurement accuracy and noise. Even when we perform measurement intentionally, the result we get may not be perfectly accurate. Real detectors have noise, random errors caused by thermal fluctuations, electric or electrical interference, and imperfect components. In quantum systems, these errors are especially damaging because the signals being detected are already at the absolute minimum possible level. A single quantum of energy is the smallest unit of information, and noise can easily be comparable in size to the signal itself, making the result unreliable. So let's dive into an example where we are trying to hear a single person speaking softly in a stadium full of people talking to at the normal volume. The signals we are trying to detect, one voice is completely buried in the noise of thousands of other voices. We may hear a voice, but we cannot be sure it is the right one. Quantum detectors face a sample problem, and it technically is the same problem. The signal from a single particle is tiny, and even the thermal vibrations of a detector itself can produce false signals that look identical to real ones. Separating signal from noise is one of the hardest problems in experimental quantum physics. The no cloning theorem. You cannot copy quantum information. This is a very significant slide, and I would like you to pay attention to this. In classical computing, copying information is trivial. You can duplicate a file as many times as you like. In quantum mechanics, it is impossible to make a perfect copy of an unknown quantum state. This is called a no cloning theorem. It follows directly from the rules of quantum mechanics and is not a technological limitation. This theorem has profound consequences for quantum measurement. You cannot measure an unknown quantum state many times to build up a statistical picture because you only have one copy and measurement destroys it. So if you receive a sealed envelope containing a message written in an unknown language, the rule of this scenario say that the moment you open the envelope to read it, the message permanently changes. You cannot photocopy it before opening. Copying is not allowed. You get one look at the original is altered forever. This is a situation with quantum states. Each measurement gives you partial information but changes the state, and you cannot go back to examine the original. Unlike the library book, you cannot photocopy a quantum state before reading it. Reconstructing a full state or quantum state tomography. Because a single measurement on a quantum state gives only one result and destroys the superposition, learning the full quantum state requires preparing many identical copies of the state and measuring each one in a different way. This process is called quantum state tomography. By collecting statistics from many different types of measurements, scientists can reconstruct what the original state must have been. It is an indirect and resource intensive process, but it is the only way to fully characterize an unknown quantum state. We can look at a use case where if you want to know the exact shape of three-dimensional sculpture, however, you can only see two-dimensional shadows of it. One shadow from the front gives you some information, one from the side gives you different information, one from above gives you yet another. By combining many shadows from many angles, you can reconstruct the full three-dimensional shape. Quantum state tomography works the same way. Each measurement is like a shadow, and only by combining enough different measurements can you reconstruct the full quantum state that cast them. The observer effect. Does consciousness matter? Here's the human in the loop comes in the quantum computing. A common misconception is that quantum measurement requires a conscious observer, that a human mind must be looking for the superposition to collapse. This is not correct. Measurement in quantum mechanics simply means an interaction between the quantum system and a larger classical system, such as a detector, a recording device, or even a single stray particle. Consciousness plays no special role. The collapse happens whenever the quantum system becomes entangled with a larger environment, regardless of whether anyone is watching or not. A camera in an empty forest will capture a photo of a falling tree, even with no human present. The camera, a classical device, records the event and the information is stored, regardless of whether anyone ever looks at that photo or not. Similarly, a particle detector in a laboratory records the arrival of a quantum particle and collapses its state even if all the scientists are in a different building. The measurement happens at the moment of physical interaction with the detector, not at the moment a human glances at the readout. Weak measurements peaking without fully collapsing. Standard measurements fully collapse a quantum state, but physicists have developed a technique called a weak measurement, which extracts only a tiny amount of information from the quantum system and causes only a very small disturbance. By repeating weak measurements on many identical states, scientists can gradually build up a picture of the quantum state without ever fully destroying it in a single shot. The trade off is that each individual weak measurement result is very noisy and imprecise of its own. So imagine you want to know the weight of a sleeping baby without waking it. If you lift the baby directly onto a scale, the baby wakes up. That's a strong measurement. Instead, you very gently press one finger against the mattress next to the baby and feel the slight depression in the fabric. This gives you almost no information on its own. But if you do it in hundreds of places and average the result, you gradually build a picture of the weight distribution. Each gentle press is like a weak measurement, minimal disturbance, minimal information, but collectively useful. So, before I finish this lecture, let me share with you the fighting decoherence idea, because decoherence constantly tries to destroy quantum information. Quantum computers must use quantum error correction to detect and fix errors without directly measuring the fragile quantum data. The trick is to encode information in a clever way across multiple qubits so that errors can be detected by measuring relationships between qubits rather than the qubits themselves. This way you get information about what went wrong without collapsing the data you're trying to protect. If sending an important three-word message, but each word might get corrupted in transmission, instead of sending the message once, you send it three times. Meet at noon, and then meet at noon, and then meet at noon. If the receiver gets meet at noon, meet at noon, meet at noon, the error in the third, it can be meet at noom, N-O-O-M, if the decoherence is happening. So fighting the decoherence. The error in the third copy, which is meet at noom, N-O-O-M, which is technically not a noon. So the error in the third copy is obviously by comparison. The original message is recoverable. Quantum error correction works on the same majority vote principle, and the error is identified by checking consistently among multiple qubits, not by reading the data directly and collapsing it. So I also would like to share something with you before I actually close the lecture in this specific, even though this says happy learning. Let's summarize the limitations of quantum measurement. The quantum measurement faces several hard limitations that are not enduring problems, but fundamental laws of nature. First, you cannot measure a quantum state without disturbing it. Second, you cannot measure two incompatible properties simultaneously with a full precision. Third, you cannot copy an unknown quantum state to measure it repeatedly. Fourth, any interaction with the environment destroys the quantum superposition through decoherence. These limitations together make extracting complete information from quantum systems fundamentally harder and extracting information from classical systems. So, if we think of a library where every book can only ever be read once, the act of reading permanently changes the text. You cannot photocopy it first, you cannot read it twice, you cannot lend it or get it back unchanged, and the books are stored in a room so sensitive that even walking near the shelves randomly shuffle the pages. Getting useful, reliable information out of the library requires enormous cleverness and planning. That library is a good analogy for the fundamental challenge in the quantum measurement. So, hope this has given you some decent thoughts. And before I close, the future of quantum measurement, despite its challenges and limitations, quantum measurement is at the heart of every quantum technology: quantum computing, quantum cryptography, quantum sensing, and quantum communication. Researchers are developing better error correction codes, more isolated qubits, faster measurement readouts, systems, and smarter algorithms that reduce how many measurements are needed. Understanding the limits of quantum measurement is not a dead end. It is a map showing where the hardest and most important engineering work still need to be done. So, final use case before I say happy learning is early radio technology could only transmit blurry signals over short distances and was overwhelmed by interferences. Engineers who understood exactly why the signal was limited, the physics of electromagnetic noise, antenna design, and signal to noise ratios were the ones who invented the improvements that made global communication possible. Quantum engineers today are in a similar position, but by understanding the precisely what limits quantum measurement, they are designing the error correction codes, isolation techniques, and measurement strategies that all will make large scale quantum computing a reality in the coming decades. Happy learning. Hopefully, you are going to be one of such researcher. See you in the next lecture.